In this first question, we have a Senate committee who is looking at healthcare costs here. They want to investigate the average rate of cost increase by type of payment. So the different types of payments are medical savings account, HMO, PPO, and then Medicare. And then also by level of care, inpatient or outpatient. So they designed the experiment with 1,000 individuals that are randomly sampled from each factor level combination. We want to identify the response variable. So that's the dependent variable. So the dependent variable is the average rate of cost increase here. And then the factors and their types. So remember, the factors are the variables. So the variables here are type of payment and then level of care. So payment type, and care level. And then the factor level combinations. And then also both of these are qualitative variables. So payment type is categories and then care level is categories. Factor level combinations. So remember, the factor is the variable and then the level is the value. So you would express these as ordered pairs of variable, comma, value. So those would look like this. So we've got a medical savings account outpatient, HMO outpatient, PPO outpatient, or Medicare outpatient, and then the same for inpatient. So we've got 4 different factor level combinations. I'm sorry, 8 different factor level combinations because we've got 4 values for the first variable of payment type and 2 values for the second variable of care level. And then they want us to identify the experimental units. That would be the 1,000 individuals. Well, actually, the 1,000 individuals is the sample. So the experimental units are the individuals in general. So that's just vocabulary. Next up, we've got a car dealership here who wants to determine which sales people sell the most based on the type of compensation. So commission only, salary only, or a combination of base salary plus commission. So you want to see the sales person where they're most productive, which of these. So we took a random sample based on previous year's records, and then the salaries were analyzed, and then we're going to complete an ANOVA table by using this data here and perform a hypothesis test to determine whether the mean sales here of the groups is the same. So that would be our null hypothesis. We're going to use the alpha is 0.10 level. So here is a partial ANOVA table. And we will use the calculator to compute and fill in our ANOVA table, and then we will make the decision on our hypothesis test. So remember here that we need to set up a null and alternative hypothesis to start. So that's step 1. So we need H0 and HA. So we're testing to see if the mean sales is the same. So that's going to be our null, is that the mean for the first group equals the mean for the second equals the mean for the third. And then HA is going to be that at least 2 means differ. So not necessarily all 3, but at least 2 of them differ. That's the opposite of they're all equal. And let's go ahead and write out our values here. And we need our critical value. So our alpha is 0.10. And then we need our degrees of freedom. So the first degree of freedom is denoted by nu1, and that is k minus 1, where k is the number of groups. So we've got 3 groups. So this is 3 minus 1, which is 2. And then our second degree of freedom here we denoted by nu sub 2. It looks like v. It's actually nu. And that is n minus k. N is the total number of data values. So here we've got 15 data values. Minus k is 3 groups. And that leaves you 12. And so then our f value, we want the f value with 0.10 to the right. We can get that from the Excel distribution calculator. So here I've opened that up. We want the inverse f tab. We will put our alpha as 0.10. Our degrees of freedom numerator, that was 3 minus 1, which is 2, so that's all set. Denominator, degrees of freedom n minus k, so 15 minus 3 is 12. So here 2.8068, approximately 2.81. And then step 3, we will compute our test statistic. So our f test statistic, f test. So we get that from the ANOVA table. So let's go ahead to the calculator. So we go to stat and then edit. And I've already entered the data in here. List 1, 2, and 3 for commission, salary, and combination. And then we go to stat and then to tests and then arrow up. Since ANOVA is the very last one on the list, press enter. And then we need to do second of 1 to get list 1, comma, second 2 for list 2, comma, second 3 for list 3, close up the parentheses, enter. So our F value 3.168, 3.17. So that's actually here, 3.17. Our p-value 0.078, so 0.079. Let's go ahead and list that. And then degrees of freedom for the factor 2, sum of squares 4195. So that's 2. The sum of squares 4195.35. We'll just do the whole number portion of that, 4195. The mean square 2097.67. So that's the 2098 here. For error, that's down here, degrees of freedom 12. Sum of squares 7945, so this will be 12. There's the 7945. 662.08 is right here. And then your total, just add these up. 2 and 12, 14. If you add these two, you get the 12,140. So there's our ANOVA table filled in. And then our test value here, 3.17. And that is greater than 2.81. And remember that this F distribution is a skewed distribution. So it looks like this. And we've got the 2.81 out here. And that has area to the right of 0.10. And that is the rejection region. And then we see that our test statistic of 3.17 falls here. Well, that's kind of a deformed 8.1 there. That's supposed to be 2.81. And then we got our 3.17, and that is in the rejection region. So this tells us that we reject the null hypothesis. And then our next step here is to go ahead and what does it mean to reject the null hypothesis? The null is that all means are equal, so no, at least two differ. So there is sufficient evidence, interpret our conclusion here, to conclude the means differ. At least two means differ. Now we don't know which two means differ. We have to do the post hoc test to determine that. But we do know that there is a difference in sales based on commission, salary, or combination. And then that was ANOVA. And then we've got now the post hoc test. That's going to actually be in the Canvas portion. So the two keys test and looking at how the means differ. And then in the last part of this unit, we looked at linear regression. So the first questions here, a little bit of review. Find the slope and y-intercept for the line that goes through these 2 points. So you would label x1, y1 and x2, y2. So your slope here is going to be y2 minus y1, negative 4 minus 2. Over x2 minus x1, 3 minus 2, which is negative 6 over 1, negative 6. And then to get your y-intercept, we'll plug that into mx plus b, y equal mx plus b. So we know our slope is negative 6, so negative 6x plus b. And then we can go ahead and plug either point in. Let's use 2, 2. So 2 equals negative 6 times 2 plus b. So 2 is negative 12 plus b. Whoops, not 21. And then add 12 to both sides. So 14 equals b. So our line here then is y equals negative 6x. Plus 14. So a little bit of review there. Next up, we are looking at a linear regression here. So we're given some x and y measurements. X is grade level and then y is reading level. So here's the data. So we first want to construct our scattergram for the data. So that's just plotting x and y. So I went ahead and already constructed our scatter diagram, and then I've got the least squares line going through there too, which we haven't computed yet, but you can double check my points here, x versus y. Hypothesize what the scattergram tells us about the relationship between x and y. Well, we can see that as x increases, y increases because these kind of channel from lower left to upper right. So it looks like there is a positive relationship here, and it looks like it is roughly linear. So, but so we could say here looks like there is a positive, and parenthetically we could say linear, roughly linear relationship or correlation. And then next up, we're going to go ahead and find our least squares line, plot it on the scatter diagram. So here's all the pieces that we need. We need to first do two variable statistics, enter our data into the TI, and then we'll need sum of squares of xx, sum of squares of xy. Our slope is the ratio of the sum of squares, And then our y-intercept, beta 0 hat, is y bar minus beta 1 hat times x bar, the slope times x bar. And then we can go ahead and list our least squares line. So let's go ahead and do that real quick. So we go to Stat and then Edit. And I've already entered the lists in here. So we'll go back to Stat and then to Calc, and we need our two variable stats first. List 1 is x, list 2 is y, and calculate. So x bar is 4, sum of x is 24. N, by the way, is 6 here. So n is 6. X bar 4, sum of x 24. Sum of x squared 124. And then y bar 3.33. So 124, we've already got that in there. And y bar 3.33, repeating. And then sum of y, down on the bottom there, 20. Sum of y squared, 74. So 20 here. And a sum of y squared, looks like we didn't need that in this portion. And then sum of xy, 91. So then our sum of squares of xy, we do the sum of x squared number, that's the 124, minus sum of x is 24, that gets squared, and just that portion is over n, the 6. And if we enter this into the calculator, and you should do that and double check me, you will get 28. Sum of x squared, sum of xy, sum of squares of xy, sum of xy, which is our 91. And then minus the sum of the x's is the 24 times the sum of y, which is 20. And then we're dividing by n, which is 6. And if you do the calculator work there, you will get 11. So then our slope, we do the sum of squares of xy on top, which is the 11, divided by the sum of squares of xx downstairs, 28. So 11 over 28, which is approximately 0.39286. And then for our y-intercept, we take our y bar there, which is the 3.333, minus our slope, 0.39286. Keep some extra decimal places in that slope until you've figured the y-intercept. And then times our x bar, which is 4. And then if you compute this in the calculator, you'll get 1.762 to 3 decimal places. So then our regression line here, mx plus b, so that's going to be well, actually, we do beta 0 plus beta 1 hat. So we'll do the 1.762 out in front, and then plus 0.393. We'll keep 3 decimal places in that slope right there, times x. So there's our least squares line. And then to plot this, you can pick 2 x values and 2 y values, or you can start from that y-intercept and you can try and do a rise run. But what I would do is I would just do x versus y and pick x is 0, and then this goes up to 4, 6, 8, and then maybe x equals 8, and then figure your 2 y values here, and then plot those, and you should get this line here. So pick 2 x's. That's usually the easiest way to do it when you have these decimal values in there, because it's a little harder to do rise and run. And then next they want us to interpret the slope and y-intercept here in the context of the problem. So remember, x is grade level and y is reading level. Okay, so our slope here, and I'll go ahead and use our familiar m, our slope, which is 0.393, and you can write that as 393 over 1. And in the numerator here, this is going to be a change in y over change in x, so change in reading level. And then down here, this is the change in grade level. So, or I'm sorry, change in age. So this is saying that for each year older, reading level increases by approximately 0.393. So each year older gives increase in reading level, so increase of 0.393 in the reading level. Oops. And then we need Y-intercept here, which actually doesn't make sense in the context of the problem. But your Y-intercept, your B here, that's the Y when X is 0. So that's the reading level, which is the Y, when X is 0. So when age equals 0. So that would be the reading level of a newborn, which is 1.76. That doesn't make sense. Newborns can't read. So sometimes that doesn't make sense in the context of the problem. Estimate the reading level for grade 4. Actually, was this grade or age here? X is grade level, Y is reading level. Sorry about that. So this is change in grade level. So each grade level, not each year older. So each additional grade level gives you an increase of 0.393 in the reading level. And then this would be reading level at grade 0. Should be, I guess, kindergarten. So not when age equals 0, but when grade equals 0. Estimate the reading level for grade 4. So grade 4 here is saying that X is equal to 4, because X is your grade level. And then if we use our least squares line here, then our Y hat value, this is just saying plug that in, 1.762 plus 0.393 times that 4. And if you plug that in, you get 8.47 approximately. So reading level of 8.47. Over what range of X values are the model predictions valid? So it's only the X values that are in the data. So from X is 1 to X is 7. So grade 1 to 7. So that's going to be your reading level for 4th grade. So we can estimate reading levels between grades, can't go much beyond the data, otherwise the model may not be valid. Might not be still linear, might be something else. So if I have you do this on the written portion, I believe I do, then I want to see the formulas. And then remember that we can double check this in the calculator. Let's go ahead and do that. So there we want to go to Stat and then Calc, and then we'll do linear regression AX plus B or A plus BX, either one of those. Here A is your slope, B is your y-intercept, and here they're reversed. Let's go ahead and do number 4. And X list is 1, Y list is 2, calculate. And there we see our slope of 393 and our y-intercept. And then we got R squared and R values in there too. So you can always double check. If I have you do this Canvas problem, you can go right to the calculator. Although I may have you give me some of the intermediates here. Problem number 5, here we're given a least squares line here, y-intercept 2.105, slope negative 0.476. We're also given n is 80, sum of squares is xx is 89.3, sum squares xy, negative 42.5, sum of squares of yy, 28.7. We're going to find s and interpret. So remember here that s is equal to the square root of SSE over n minus 2. And then remember here that our SSE, actually probably should go ahead and bring this down below. So our SSE is sum of squares of yy minus beta 1 hat, our slope, times the sum of squares of xy. So our sum of squares of yy right there, 28.7. So I've given you some of the intermediate calculations here. And then minus our slope, negative 0.476, times sum of squares of xy, which is the negative 42.5. So we've got 3 negatives in there. And so we could do 2 negatives there would make a positive. And then if we enter this into the calculator, we get 8.47. So that goes in here. So this will now be square root 8.47 divide by 2. Divide by n minus 2. N was 80. So that'll be 80 minus 2. And if you enter that guy into the calculator, you get 0.330. And then our interpretation here is that we would expect 95% of our y values to be within 2s, which is 2 times the 0.33, which is 0.66, of the y hat values, the predicted values. So that S is looking at the error of our y values from the, of our y hat values from the y values. Next up, we're conducting a hypothesis test here to determine whether x and y are linearly related. Use a one-sided test with alpha as 0.05. So first we need our null and alternative hypothesis. So if they are linear related, then they'll have a non-zero slope. So we start with HA. So we're doing a one-sided test. Our estimated slope here was negative 0.476 right there. So our one-sided test will test beta 1 less than 0. That's what we're trying to establish. If that's not the case, beta 1 will equal 0. So linear relation, you're testing equal 0 against either less than, greater than, or not equal. Since they told us one-sided, the natural is less than 0. Now, if we had a positive slope here, we do greater than 0. If we're doing two-sided, it would be not equal 0. And then our t value here, alpha is 0.05, so t of 0.05 is going to be inverse t. So use inverse t to find that value. So that's the t value with 5% of the area to the right. So that means the left area is 95% of the area, so 0.95. And then our degrees of freedom will be n minus 2, so 80 minus 2, 78. So that is n minus 2. And if we put that into the calculator, we'll get 1.665. So we got our null alternative, we've got our critical value. Now we do our test statistic, so that's t-test. So that is going to be beta 1 hat, remember, divided by s over the square root of sum of squares of xx. And then remember where I am getting this from. If we go to the exam 5 formula sheet, here's the test for model utility for simple linear regression. That's what we're doing. So there's our H0, H1, and this is where I got the test statistic formula. So our rejection region will reject if t is less than negative t alpha. And then degrees of freedom are going to be n minus 2 there. So our beta 1 hat here, that is the negative 0.476. And then in the denominator, s is 0.33. And we're dividing by square root of sum of squares of xx, right there, 89.3. And then if you do the calculator work there, you will get negative 13.63 to 2 decimal places. And here's our t alpha, our t.05, and this is less than negative 1.665. So it's less than our critical value. So that's telling us that we reject the null hypothesis. So if we reject the null, that means we're going to conclude the alternative. So our conclusion is that there is sufficient evidence to conclude that x and y are linear related. In other words, beta 1 less than 0 is what we're concluding. So that's our test for model utility. Next up, we are finding a 95% confidence interval for beta 1 hat. So again, if we go back to our formula sheet here, here's the confidence interval for the slope, beta 1. And that's this expression here. Where your t alpha over 2 is based on n minus 2 degrees of freedom. And this expression right here, that is our standard deviation for the beta 1 hat sampling distribution. So go ahead and paste in that confidence interval formula. So actually, let me scooch this back up a little bit. So our beta 1 hat, that is our slope, the negative 0.476, plus or minus, we need our t alpha over 2. So alpha is 0.05. So that tells us that alpha over 2 is 0.025. So then we want t 0.025. So that means 2.5% of the area is to the right. So 97.5 is the left area. So we want to do inverse t 0.975. And then degrees of freedom, 80 minus 2, 78. And if you enter that into the calculator, you'll get 1.991. So 1.991 is our t-value, and then times this s over sum of squares of SSXX, that's right here. So 0.33 over root 89.3. So that's negative 0.476. And then if you compute this margin of error here in the calculator, you will get 0.070 to 3 decimal places. So plus or minus 0.070. So if you subtract the 0.070 from the 476, you'll get negative 0.546. And then if you add the 0.07 on, you will get negative 0.406. So we're 95% confident that beta 1, the actual slope, population slope, is in this interval, which does not contain 0. So that is statistically significant. Next up, we are finding r and r squared, coefficient of determination, and correlation and determination. And then does your value of r agree with the results of the hypothesis test? So the hypothesis test said that they were linear related. So let's go ahead and find our r and r squared. So again, go back to formula sheet here. So r squared, we can use this formula if we want, or we can just find our r value and square it to actually get the same thing. So r is up here. Or is it? There it is, right there. So let's go ahead and grab our r value here. So there's r, and then let's go ahead and grab our r squared value. We could use this one if we want. Okay, so let's go ahead and compute those. So these values were given up above in the problem statement. So the sum of squares of xy was negative 42.5. Right, all of these are given up here. Right here, xx, xy, and yy. That's where I'm getting those. So in the denominator, square root of sum of squares of xx, that's the 89.3. And then the sum of squares of yy, that's the 28.7. And if you plug this beast into the calculator, you'll get negative 0.84, pretty close to negative 1. So this is a strong negative linear relationship is how you would interpret that. And then r squared here, so our sum of squares of yy, that is 28.7, minus the SSE. SSE was 8.47. Found that up above. And then all over the sum of squares of yy, again 28.7. And that gives 0.705. And then also notice if you take our r value here, negative 0.84, and square that, you also get the 0.705. And remember what that 0.705 means. That means 70.5% of the variation in the data is explained by the regression line. And that's a fairly high percentage. So, and then the other question was, does your value of R agree with the results of the hypothesis test? Yes, it does agree. So this had strong negative linear relationship, and up above in the hypothesis test, we got a test statistic that was extremely negative. So, and we rejected the null hypothesis, concluding that there was a linear relationship. So they both indicate a negative linear relationship. So the last question is yes, both indicate negative linear relation. Okay, so that should put you in pretty good shape for the in-class exam.